All right, so for our first example of a integral of a vector field over a curve, we're going to find the work done by this force field here, x, y, yz, zx, when moving a particle along the twisted cubic. So that's the name for this path right here, t squared t cubed. The reason why is because if you, let's see, what does this thing look like? So suppose that's the y-axis and that's the x-axis. So then if you had a parabola and xy plane looking like this, then you started off somewhere down below and you came up engaging with this path, and then as you go around, go back up the far side. That's the path we're looking like. So if I were to stand over here and look at it, what I would see is the graph of a cubic going upward like that. But it's kind of wrapped around this parabola, so hence twisted cubic. Okay. All right, so our work integral is by the formula that we just concocted on the last page, f dot dc. So we look at this and we say, okay, so our parameter domain is 0 to 1. So that's going to set us up as an integral from 0 to 1. And then we have f, which is, let's see, so it's got all these x's and y's in it. So the thing to do is take this data right here and extract this as x equals t, y equals t squared, z equals t cubed, and substitute all of this into the force field. So that's going to give us, let's see, so we get t and t squared give us t cubed, and then t squared times t cubed gives us t to the 5th, and then t cubed times t gives us t to the 4th. So there's our new and improved version of f. And then the next thing, so this is f in coordinates. Maybe I should say f of c of t. And then the next thing we need is the derivative of c. So to put in here c prime of t, we just differentiate term by term. So the derivative of t is 1, the derivative of t squared is 2t, and the derivative of t cubed is 3t squared. And then we have dt. And so we work out this dot product. And so we've got t cubed matched with 1, so that's going to give us t cubed. And then we've got t to the 5th matched with 2t, so that's going to be 2t to the 6th. And then we've got t to the 4th matched with 3t squared, so that's going to be 3t to the 6th. And this is all dt, and hey, look at that. What do you know? Now it's just an integral of a single variable, and we're back in Calc 2, and it's no problem, and you work it out, and it's 27 over 28. The end. So now we can break this a little bit down and kind of say, hey, what happened with this process? And so I'm going to talk about kind of different ways to write this integral, and this is a little bit pushing notation around, but hopefully it kind of connects the dots, and so you can see kind of what happens. So in the beginning, we started with f dot dc, right? So this guy is the line integral of a vector field, right? And sometimes this is also called vector differential form. Okay, and so then what we did is we said, what do we have here? So if I look at what the parts of these things are, then f looks like xy, yz, zx, and it's being dotted with this vector that looks like dx, dy, dz. So the idea here that I'm using is that dc can be written as dx, dy, dz in terms of those differentials. So this is why it's called vector differential form. Then when we do that dot product, what we get is the integral over c of xy times dx plus yz times dy plus zx times dz. And so this guy is now the line integral of 3 scalar fields. Right, the stuff that we were doing in the last couple of clips. Okay, and so this one is sometimes called scalar differential form. All right, and all of this is before we attach a parameterization. So when we attach a parameterization, dc now becomes c prime of t dt, and everything is in terms of t. So we have x prime of t, y prime of t, z prime of t dt, and this integral becomes now an integral. Actually, let's do it as if we drop it down a level here when we introduce the parameterization. So now we have the integral from a to b, and we have x of t, y of t times dx, which is x prime of t dt, and y of t, z of t times dy, and z of t, x of t times dz. And there we go. And so then that's everything written fully out. And so by the time we're done, we have transformed everything into one giant single variable integral from Calc 2. Everything is with respect to dt. And the reason why it's one-dimensional is because the path that we're moving along is a one-dimensional object. It might curl around in R3, but it's just a one-dimensional path that we are integrating over.